And we're back. We're going to do a little bit of mechanics, and in this case it's going to be simple harmonic motion. This is basically when you have oscillations, when you have a spring is kind of the main example of simple harmonic motion, which is bouncing back and forth. By definition, it's basically a type of motion. It's a periodic motion, almost like a subset of periodic motion, where the oscillation is caused by forces proportional to displacements. So the spring is perfect. We've got Hooke's law, the force is negative kx, where the x is your displacement from equilibrium. So things like tuning forks, springs, more or less a pendulum which is swinging back and forth at a small angle. Pressure waves that you get out of organ pipes. There's different examples like this for simple harmonic motion. So basically what we're talking about is when an object is bouncing back and forth between two endpoints, and those are called the amplitudes. That's your maximum displacement. So at either amplitude, we're basically talking about your maximum x position. These are the points where you stop, so your speed is 0. You have a maximum force because your force depends on displacement, and therefore you have a maximum acceleration. So those all go in hand. At equilibrium, the midpoint between the two amplitudes, you have your minimum displacement, so there is no displacement. You're moving the fastest, and your acceleration is 0 because the force is 0. So conceptually, that's kind of what happens, and anywhere in between, you have combinations of all this stuff. So what we want to focus on here is Newton's law. We want to try to figure out how can we describe this motion in terms of time. So it's easy enough. We're assuming no friction forces. And so the Newton's law would simply give you your net force is the spring, negative kx. So this gives us the acceleration, is dividing through by the mass. And that's all fine and good. We can certainly see this is non-constant. As your x value changes, and so does your force and acceleration. But how do you get time in here? What we have to do is realize the definition of acceleration. We're most used to seeing that it's the rate of change of your velocity. We write it as dv dt. Now the trouble is, velocity is a derivative as well. So we're taking a time derivative of a derivative of position with respect to time. And so hopefully this notation makes a little sense. It's almost like you're multiplying the d's together to get a d squared, and x on top. And then you have a dt squared in your denominator. A standard notation is what we call a second derivative. So if I substitute that in for the acceleration, f equals ma suddenly looks kind of weird. It's a little more difficult. It's a second order differential equation. How in the world do you solve for x? Well, you can't really separate the variables. It doesn't work the same way as it does when you have just a single derivative. There's no integrals that can take care of these higher order derivatives. It just doesn't exist. So what we have to do is try to figure out a way of sort of guessing at what x could be. Because ultimately, really, what we're after is this. What's the function of x in terms of time? So the way I like to think about it in the physics point of view is, if you think about what we're trying to describe physically, it's periodic motion. Well, if you want to describe that mathematically, you probably want a periodic function. Things that could do that are sines and cosines. Another way to think about this, in terms of a mathematician, would be you want to function that you can plug in, and when you take two derivatives, you get the opposite of itself. Sines and cosines satisfy that. So what we can do is try to generate a function, a solution to this. Let's try sine, why not? We know time's got to be part of this. And as we build this solution, we have to realize that you can't do something like the sine of 3 seconds. Okay, that doesn't make any sense. You can't do it. We need another factor in here where this omega thing is familiar if we've done rotations. It's something that has to have units of radians per second. Because when you multiply that by time, you just get radians, and that's something you can find the sine of. You also need units to work out. We know that sine oscillates between a maximum and minimum. In terms of position, our definition for that is amplitude. So this is a kind of a generic solution. We could have also said it could have been a cosine. Oops. But now we have to get a little more specific. What in the world is this this omega thing? Well, let's take derivatives. Your velocity equation is going to be a derivative of this x solution that we guessed at. And we can do that simple enough. Because of the chain rule, omega comes out, and we get a cosine. We can take another derivative, and let's see, cosine gives us a negative sine. We get another factor of this omega thing coming out, and we get sine back. So now if we go back to the original equation, up here in the box, on the left hand side we have acceleration. Well, that's negative a omega squared sine of omega t. On the right hand side we have some constants, negative k over m times x. Well, x is a sine omega t. The sine drops out, the minus signs go away, and what this tells us is the solution works if omega squared is spring constant divided by mass, or omega is simply the square root of the spring constant divided by mass. Okay. It has units of radians per second, and we call this the angular frequency. The last thing I'll say here is make a couple connections. We can relate this to normal frequency, like the hertz, how many bounces per second, by a factor of 2 pi. Now we also know from things like waves and just general definitions that frequency is the reciprocal of period. This is also 2 pi over the period, okay, the time it takes to bounce back and forth. Now if we solve for the period using these two expressions, we get another thing, another little expression. It's going to be a factor of 2 pi times the square root of m over k. So this is what we can use to find the period of a spring. It depends directly on mass. So the heavier the mass, the longer it's going to take. The more inertia you have, so the harder it is to move the thing. And it's inverse with the spring constant. So if you have a really tight spring, you're dividing by a big number and it's going to oscillate really quickly. And if you have a loose spring, a lower k constant, spring constant, it's going to take a longer time. So this expression actually makes sense, and in labs in class we actually sort of derive that from your data after doing some fits. So in the end, we're talking about oscillations, so these terms of frequency and period come into play. We've found this expression here, this angular frequency idea, which depends on the mechanical properties of the spring. We've got sines and cosines as solutions, the mathematical solutions to this kind of motion. So hopefully this makes a little bit of sense. This is the essence of simple harmonic motion. Notice that the frequencies, these expressions that we have down here, do not depend on the amplitude. So one last little graph that I'll put here. If we're plotting your position as a function of time, let's say, you may start off with a large amplitude, big bounces. But in reality, that amplitude is going to die down. It bounces less and less and less. But at the same time, the wavelength and the frequency don't change. Okay? This is another feature of harmonic motion. The amplitudes decrease because of friction forces and losses of energy. But the frequency, the angular frequency, and the period stay constant. So a bouncing spring or an oscillating, a swinging pendulum can be used to make clocks. Even if their amplitudes die down, it doesn't matter. They still keep time. Okay. So in the end, yeah, lots of little things pop out from a very simple phenomenon of just a mass bouncing back and forth on a spring. So until next time, we'll see you later.